Welcome. Let's quickly look at calculus in 4 dimensions. One of the motivations to study calculus in higher dimensions, 4 dimensions or higher, is physics. So when we have coordinates x, y, z, and maybe the fourth coordinate is time, so this is physics, relativity, time, and we have a point in R4. Another motivation is computer vision or computer graphics or art. When you look at perspectives and you look at geometry of computer vision, you often do things in projective spaces. So this is computer vision. So when we look at the projective space, so these are all lines in R4. There's a lot of advantages because projective geometry, three-dimensional projective geometry, is actually affine geometry in R4. So you can use linear algebra here to study this, and that's very useful, very powerful. There is another motivation which comes from algebra, which is that R4 is actually the quaternions. Space of quaternions, and so it's the largest division algebra, largest division algebra which is associative. Largest associative division algebra. So the list is we have the real numbers and we have the complex numbers, we have the quaternions, and then we have the octonions. The octonions here are no more associative. So this is the largest associative division algebra, and it's very important because here in the quaternions we have a sphere. So the unit sphere in R4 is this is SU2. It's the gauge group of the weak force. So it's a very important thing, and it's also the largest, actually it's the only space where the unit sphere is a non-abelian Lie group. So this is a Lie group. No other space has these properties. Here we have the circle. The circle is a Lie group, but it's commutative. This is non-commutative. Here it's no more a Lie group. So maybe the most famous object in 4-dimensional space is the hypercube. So tesseract. We cannot visualize this directly in 4-dimensional space because we cannot look there, but we can project it into 3-dimensional space, and then we see this picture. So that's it's a cube inside a cube, and you connect it here. So it's an iconic object, and it's one of the Platonic solids. So if you look at the polytopes, so there are 6 polytopes in 4 dimensions like this. There are 5 polytopes in 3 dimensions. There are 6 in 4 dimensions, and then in 5 dimensions and higher there are only 3. There's only the analog of the cube, the analog of the tetrahedron, and the analog of the octahedron. So 4-dimensional space is kind of also there the most 6. There are 6 of them. Schläfli has classified them first. And another thing which is interesting is the sphere. So this is the 3 sphere. So that's all the x squared plus y squared plus z squared plus t squared is equal to 1. So we can look at that. So I mentioned this already. This is a very important sphere. This is the hypersphere, also called, and it's SU2, one of the gauge groups. It's a very important object, and we can parameterize this like we can parameterize spheres in 2 dimensions, 3 dimensions. What we can get, so we have a r phi theta psi We can take, for example, we can take cosine theta, cosine phi, cosine theta, sine phi, sine theta, sine psi, and then cosine theta, sine psi, sine theta. So if you look at that, that's your x, y, z, t. And you can check that this is, if you sum up this, you get cosine squared psi. If you add up the squares of that, you get sine squared psi. You add them down, you get 1. So this is a parameterization of the and so we can do calculus like before. We can compute the surface area volume. So that's 2 pi square here for the volume. And you can say, actually in this case, what we have is phi is between 0 and 2 pi. Theta goes from 0 to 2 pi, and the psi goes from 2 pi half. So that's a Hopf parameterization of the 3 sphere. We will come to that. I want to actually make a computation there, kind of use Stokes' theorem here. But there are other things we can look at. We can, for example, look at the 3 torus. So the 3 torus, it's like the analog of the donut. That's kind of what we call T2. The 3 torus is what we call T3. It's the circle times the circle times the circle. And we can also parameterize this in R4, theta psi, like we did in so it's 3 plus cosine psi, cosine phi. We just take add 3 cosine psi, sine phi, 3 plus cosine sine sine psi, cosine theta, and 3 plus sine psi, sine theta. So that's a parameterization of the. So now everything goes 0. Phi, theta, psi go all from 0 to 2. So that's a nice object. We can calculate with this also. We can compute everything. We can compute the volume. We can compute. We can do integral theorems, etc. And then there are also other objects like the planes, right? If you have ax plus by plus cz plus dt is equal to E. These are hyperplanes. You can look at surfaces, right? In general, we have g, x, y, z, t is equal to constant. These are level surfaces. These are actually three-dimensional. These are three-dimensional objects. These are 3 manifolds. For example, we can look at x squared plus y squared is equal to 1, which is a kind of a hypercylinder. Or we can look at x squared plus y squared is equal to 1, and z squared plus w squared is equal to 1, which is actually a 2-dimensional. In this case, we have a 2-dimensional, also a 2-dimensional torus. So there are 2-dimensional objects. 1-dimensional objects are curves. We can look at curves. R of t. So we have an x of t, y of t, z of t. I'm running out of letters. So t of t. Let me just call it w of t. So when we use t as a parameter, of course we are in trouble if you use t as our 4th coordinate. But you get the idea. So we have all these objects. Let's now look at calculus, how we actually generalize the grad curl diff to higher dimensions. In order to generalize calculus to higher dimensions, especially derivatives, we have to introduce differential forms. So it's no more just scalar functions and vector fields. What we have is 0 forms. So these are scalar functions. Call this f, like a scalar function. Now we also have one forms. So one forms are f. We write them like this. Either we write them as in vector form p, q, r, s. But it's more convenient to actually write them down in the following form: p dx plus q dy plus r dz plus s dt. So we will see this dx, dy, dz, and dt have a precise meaning. They are actually maps which map a vector into a scalar. So these are linear maps. But for now, just look at it as a kind of just a notation, like we have used ijk in the case of three-dimensional calculus. So these are just. Now we have also two forms. Now what we actually write, we write it like that. So I write it as a dx dy plus b dx dz plus c dx dt plus d dy dz plus e dy dt plus f dz dt. You see, these two forms have there are two kind of dx dy. They come in pairs here, and we have a rule which says dx dy is minus dy dx. Usually there is the usual notation is with this wedge symbol, but I'm skipping this because it gives us just too much to write. So this is the rule. If we switch dx dy, we actually switch around we get the negative sign here. So there are 6 components here. There are 6 ways to choose 2 elements from. So if you take 2 elements from 4, this is 6. This is the binomial coefficient 4, 2, which is 6. There are 6 elements here. So here we have 4 elements. Here we have 6 elements, and then there are 3 forms. Which is f is equal to a dx d. Actually, I write it like that: dy dz dt plus b dx dz dt plus c d x dy dt plus d x dy dz. So you see, there again, there are b, 4, 3. Choosing 3 elements is again 4. So choosing 1 element from 4 is 4. Choosing 0 elements is 1. And then we have the 4 forms again. 4 forms. This f is equal to a dx dy dz dt. So if we look at this, so it's much richer structure in 3D, just as a comparison. In 3D, so we have the 0 forms f, we have the 1 forms f is equal to p dx plus q dy plus r dz. So that's what we call the vector field. And then we have a 2 form. So f is equal to p dy dz plus q. Let me just use a, b, c here, just to make sure. So it's a, b, dx dz plus c dx dy. You see that the 2 forms again can be associated with vector fields. So we usually kind of call this in our multivariable calculus courses, we call these vector fields. But we lie to you. We actually identify this with this. It's a completely different object here. But then we have a 3 form. We have f is equal to a dx dy dz. Which also we lie to you, this 3 form is actually identified with 0 forms. So what we have is kind of in we just tell you in calculus that these are scalar fields, throwing them in the same bin, and this we also throw in the same bin here. And so that's in 4 dimensions. We have it's the transition from 3 dimensions to 4 dimensions, which shows us really that something has to go on, right? It has to be changed. So you see in the Pascal triangle, it's the first time that we get here something else. We get something which is not kind of a vector field. Well, physicists know that in physics the 2 form is actually electromagnetic field, E and B together. If you look at E and B together, that's actually a 2 form. There's 6 components, 3 electric fields, 3 magnetic fields. So it's actually a 2 form. So in 4 dimensions everything becomes much more natural. But so you ask yourself, why do we do that? One of the reasons is that now the derivative we can define very, very naturally, and we have not to invent it for every possible thing. We don't have to invent the curl and the divergence and all this. Is all very natural. Let's just look at that. So let's look at the notion of the derivative, the gradient. So we have a 0 form f. What we do is we take the derivative, we get df, which we call the gradient of f. So that's fx dx plus fy dy plus fz dz plus ft dt. So you see, it's kind of the thing which we usually kind of would call fx, fy, fz, ft. But we leave that with the dx, dy, we see y. So that's the gradient. Now let's look at the curl. So what we have is a 1 form. So it's p dx plus q dy plus r dz plus s dt. So what we do is we define the curl of f. Now what we do is we just essentially take this gradient for p, and we use the rule that dx dy is minus dy dx all the time, and that's especially when dx dx is equal to 0. So this is a kind of a rule for this this dx. This is the curl. Okay, let's compute the curl. So the curl of f. What we do is we take this p and we take the derivative like in the gradient there. So we get px dx dx plus py dx dy dx plus pz dz dx plus pt dt dx plus, now comes this, we take the derivative here, so we get qx dx dy plus qy dy dy plus qz dz dy plus qt dt dy plus now rx dx dz plus ry dy dz plus rz dz dz plus rt dt dz. And finally here we have sx dx dt plus sy dy dt plus sz dz dt plus st dt dt. Now this algebra, of course our exterior algebra, dx dx is always 0 here. It has to do with the Pauli principle. You cannot have two things in the same state here. When you switch to this, the sign changes. So we can actually, what we have is we can put things together. So what we have is we can write this, let's take everything with dx dy together. So dx dy appears here. So dx dy appears here and here. So this is equal to qx minus py dx dy. So we have switched here the sign. Then the next thing is, let's look at dx dz. So dx dz appears here, dx dz appears here. So what we get is plus rx minus pz dx dz. Now we look at the term xt. Xt is here. So this is minus pt, that's here. So this is S6 minus pt plus S6 minus pt and then we have dx dt. So these are already 3 components of this 6-component 2 form. Now we have more terms. We have dy dz, which appears here. Dy dz appears also here. So it's ry minus qz dy dz. And we have 2 more terms. So let's look at the yt. So that's here. Yt appears here. Yt. So it's sy minus qt plus sy minus qt dy dt. And there is one more term, which is just what is left here, which is the zt part, which is here. So it's sc minus rt dz dt. So that's the curl. So the same thing is also just in comparison 3D, when we have f is equal to p dx plus q dy plus r dz, then we have the curl of f. So we get px dx dx plus py dy dx plus qx dy dx dy no dx dy plus qy dy dy, and actually there's also a z. So that's plus pz dz dx plus qz dz dx, and then plus rx dx dz plus ry dy dz plus rz dz dz. And this rule here tells us that these guys are going away here, and so we can put them together, dx dy. So that's actually qx minus py dx dy plus, and then we have the dx dz, which is here, rx minus pz dx dz, and then the last one is dy dz plus ry minus p yz. Where is that? Yz. So that's yz and dz dy here. So this is minus qz dy dz. Now if you take dx dy dy dz and dz dx, then you get the usual curl here. So this is actually, these are the coefficients of the usual curl. So let's look at the 2 form, and we want to get the 3 form. I might not write down everything because it's quite a hike, but we will see we get the 3 form, which has again 4 components. So what we have is the hypercurl. Let's just call it hypercurl of f. So what we do is we take ax dx. Dx is 0. That's kind of also one of the rules. So we get az is the first non-zero term, dz dx dy plus at dt dx dy. So that was this. So that was the first one, and then plus, and then we have by dy dx dz. Again, the dx goes away, the dz goes away, and then we have only dt dt dx dz. Now we have the c, the first thing which is not vanished, dy dx dt plus cz dz dx dt. Then we have plus dx dx dy dz plus dt dy dz dt. Sorry. T dy dz. So it's always first. Dy dz. Then plus ebx dx dy dt plus ez dz dy dt, and finally plus fx dx dz dt plus fy dy dz dt. So you see, these are all the terms which are non-zero, so we can put them together. Dx dy dz is yellow. Then the dx dy dt is red. Then the purple is zyt. Zyt is purple. And then the blue one is that. So let's just see what we actually have to enter here. So the x dy dz, so that's the yellow ones, x, y, z, that's actually a z belongs there. X dy, that's minus by, and that's just plus dx. So that's the first term. So the red ones are x, y, t, that's the same, at. Red one is x, y, t, that changes, minus cy, and x here, x, y, t, that's right, plus dx. Now here in the blue one we have dx dz dt. Blue one is dx dz dt, so minus cz here. Dx dz dt is bt. And x dz dt plus fx. And finally the purple one is yzt. So yzt, that's the dt. Yzt minus ez plus fy. So you see, it's a little bit of hike, but we see that the hypercurl of a 2 form is a 3 form. And finally, what we can do is we can look at the divergence. Okay, we have finally we have f is a 3 form. A dy dz dt plus b dx dz dt plus c dx dy dt plus d dx dy dz. So we have a 2 form, 3 form. So the divergence of f what we do is it's exactly the same thing like before. So we say AX, that's the only thing which is non-zero here, dx, dy, dz, dt. The AY, dy goes away, etc. So in this case, the only thing which is actually non-zero is dy, dx, dz, dt, plus cz, dz, dx, dy, dt, plus dt, dx, dx, dy, dz. Now, you see there's in every term there's a dx, dy, dz, dt. So we can actually put this together. So this is ax. This is switched, so it's minus by. This is plus cz minus dt, dx, dy, dz, dt. So we see here kind of it looks like the divergence in 3D, but there's not minus signs coming from the permutations. Just as a comparison in 3D. So that's the right way to put that in 3 dimensions. And now what happens is with the divergence of f, what we get is ax dy dx dy dz plus, now the bx dx that goes to 0, by is the only thing which is not, dy dz dx, and then plus dz dx dy. Now we can permute things around if it's rotate things around. If you have 2 permutations, that's a rotation. So we have actually then ax plus by plus cz dx dy dz. And that's usually what we call the divergence in 3 dimensions. So you see that it naturally generalizes, this framework naturally generalizes, and it can be generalized to any dimension. Okay, so in 1-dimensional calculus we have just the usual, you know, from a 0 form. From a 0 form we go to a 1 form by just taking the f prime. So what we have is f goes to f prime dx. So that's from a 0 form to a 1 form. That's the usual derivative. So here we have the gradient. The gradient which we know in 2 dimensions, right? So the gradient is fx fy. So f goes to fx dx plus fy dy, and that's a 1 form. So that's what we call the gradient here, and that gradient works in any step in this first step. When we go from a 0 form to a 1 form, it's always called the gradient. Now in 2 dimensions we have seen the curl. So that was the curl, the 2-dimensional curl. So what happened is in 2 dimensions when we have a 1 form, so in 2 dimensions when we had a 1 form, f is equal to p dx plus q dy, then the curl of f is py dy dx plus qx dx dy, which is equal to qx minus py dx dy. You see the qx minus py? That qx minus py, that's the 2-dimensional curl. So that's the reason, and it works perfectly fine in this framework here. So that's the 2-dimensional calculus. So this is 2-dimensional calculus. Now in 3-dimensional calculus we have also worked and illustrated this also with this differential form thing. So we go from 1 forms to 2 forms. By chance the 2 forms again have dimension 3. So that's the curl. And then we have from 3 dimensions we go to the divergence. So that's the divergence. So that's 3-dimensional calculus. And so what we have here in 4 dimensions, so we have the curl. That was I call this the hypercurl. I don't think there's just usually called the exterior derivative, but I call it here the hypercurl. dual curl kind of some sense, and that's the divergence. You see, here we can no more lie to you. We can no more say, okay, these are vector fields here. So we have vector fields. We have something different here. We have two forms. So this is one forms, two forms, three forms, four forms. And you can check with that in general what happens is if you take these derivatives. So these are called derivatives. So df, this is called the exterior derivative. So it goes from k forms to k plus 1 forms. Now if you do it twice, df, that's always 0. So if you take the hypercurl of the curl, that's 0. The curl of the gradient is 0. Divergence of the hypercurl is 0. And you can check that it's just because of that algebra which is anti-commutative. So dx dy is minus dy dx. That these things are 0. But it would continue like that, right? You would actually do 5, 10, 10, 5, 1. So in 5 dimensions you would have two forms which are 10-dimensional. And again 10-dimensional here, 3 forms, and 4 forms are again 5-dimensional, and 6 forms are again 1-dimensional. Kind of have one component, scalar. So these are the scalar, kind of this we identify with scalar parts, even so these are volume forms here. These are the 1 forms, 2 forms, so 1 forms, 2 forms, 3 forms. So this is the structure of the derivatives. Now we have also to integrate. Let's just see that quickly, and then we have the integral theorems. In order to define integrals, we have first to have objects to integrate over. So there's one-dimensional objects which are curves. So what we do is we take an interval and then we map it. Let's call this the variable u. We call it r of u is equal to x of u, y of u, z of u, p of u. That's a curve. And what we can do is if you have a one form, so what we can do is we can just say integrate over this is our g here. Gf is actually just what we have is we just take p times we apply dx to that. So this is px prime. So integrate u plus q y prime u plus r z prime u plus s t prime u du. So this is the line integral, what we call a line integral. If we integrate a one form over a one-dimensional curve, this is a curve in 4D. This is r of a. This is r of b. It's a curve, and we can define it. It's exactly the same definition like we have done in it's a dot product, some sense between the velocity and that vector. So that's exactly the same thing. But now we think about this kind of differently. We think about dx. So we take dx and we apply it to a vector, a vector v. That's actually just v1. So that's the rule here. Now we have surfaces also. So g is now as two variables uv. We map it into a surface. This is a two-dimensional surface, r of g. And what we do is we have a two form now. So f is a two form. So what we can do is we can just pair every, so f, for example, f is equal to maybe just a dx dy. So what we do is we think about this dx dy as a multilinear map, which is anti-commutative, which applies to the RU. This is the vector. This is the vector value. This is the parameterization. And so we say here this is equal to A, and then so when we have that, so when we integrate that, so when we integrate over GF, that's actually just the integral over G, and then we take A of R of U of V, and then this dx dy actually then becomes the RU, first component of RU, and then this is, and then RV, second component. So we apply this. So what we do is, now we actually do this dx dy, we can apply this dx dy to RU and RV. Let me just explain what this is. So we have RU, it's a vector, and RV is a vector. And then x and y are the first two components. So what we do is we take the determinant of this part. So dx dy RU RV is just the determinant of that matrix where we have RU1, RU2, RV1, RV2. So this is a little bit hard to explain, but that's what we do also when we compute the flux integral. So what we do is we think about this as the dx cross dy, so it's kind of the perpendicular to it, and then we take a volume. So this is our flux integral given by, this is the parameterization here, and then we have a three form like A dx dy dz. That's kind of one component of that. We can integrate this over G. So what we do is it's a triple integral over G, and then we have A of R of U V W, and then we take the dx dy dz and apply it to R U, R V, and R W. So this is a multilinear map which maps these three vectors into a number, and when we commute two, we get the negative sign. It's a determinant. So what it is, it's actually, what is that? That's dx dy dz applying to RU, RV, RW. If we write these three vectors down, so this is RU1, RU2, RU3, RU4, RV1, RV2, RV3, RV4, RW1, RW2, RW3, and RW4. And so what we take is, when we take this dx dy dz, we actually take this determinant of that. We can take the determinant of that. And so then we integrate the du dv, dw. So that's the three-dimensional flux. So that's what we do when we integrate a three form over a three-dimensional manifold, which is given by a parameterization. And the same thing works in with four forms. An F of 4 form you can just integrate over G. So integral G F dv is actually just integral over G. So we have F dx, dy, dz. So it's actually just, think about this like a scalar function which we integrate over this four-dimensional space. So the first theorem is the fundamental theorem of line integrals, which looks exactly the same in any dimension. So what we take is we can take the gradient, which is a one form, so which is the gradient, so df, that's f, that's a one form. And we write here, this is actually just df. So this is the theorem we are very familiar with. Now, if we have a two-dimensional surface, so this is a surface, 2D surface, and f is a one form, then df is a two form. A two form we know how to integrate over a two-dimensional surface, and so what we get is if we integrate over S, actually let's call this G. So G df, let's just call it df. That's just the integral over the boundary f. So the boundary curve, we can integrate the one form over the boundary curve. This is Stokes' theorem. Now there is a hyper-Stokes theorem which is new. So when we have a G is a 3D surface and f is a two form, so df is a three form, so we can integrate over G df, and that's the same thing if you integrate over the boundary, which is a boundary surface. It's a two-dimensional boundary surface f. So that's called hyper-Stokes. And finally we have the divergence theorem. So if G is a 4D region, delta G is a 3D boundary, f is a three form, and df is a four form. So we can integrate over that df. And that's the same thing than the triple integral over the boundary of gf. And that's the divergence theorem. This is the fundamental theorem of line integral, Stokes, hyper-Stokes, and divergence theorem. So there are four theorems. Okay, let's organize this according to dimension. So in dimension 1, so there's only one theorem there, the fundamental theorem of calculus. Now in dimension 2, there is the fundamental theorem of line integral and green. So that's two-dimensional calculus. And then there's three-dimensional calculus, where we have the fundamental theorem of line integral, we have Stokes, and we have Gauss, divergence theorem. Now this in 4 dimensions, now we have the fundamental theorem of line integral, we have Stokes. I call these hyper-Stokes. It's actually just a dual version of Stokes. And then we have again Gauss. So we see we have 4 theorems in dimension 4. And this is associated to the curl, this is associated to the hypercurl, this is associated to the derivative, and it's all organized with this Pascal triangle type structure.